everyone. I'm happy to see full hall. I've never talked to such large audience. I'm a little shy. My presentation is about vulnerability, a vulnerability in the kernel. And to begin with, well, it's a rather old story, but nevertheless it's interesting because you can make some conclusions. First of all, I can talk about it, and I can talk about the conclusions that we've made because of the experience that we gained, and what kind of steps we made for such to avoid such vulnerabilities in the future. What kind of kernel I'm talking about? We in Kaspersky develop our own operating system, and I am going to answer the question. It's not Linux. We have our own micro kernel, which was written from scratch. And second, you cannot have non-vulnerability in a vacuum. You will always be vulnerable to a certain type of attacks. Linus Torvalds once said that vulnerabilities are just bugs. And from the developer's point of view, that is true. And it's very important, therefore, to pay attention to bug detection at every stage. The most expensive bugs are created at the design phase, at the very first initial stage of the project, when you build diagrams, when you decide what has to be isolated and where. If you develop large modules, you build a threat model. And from the viewpoint of those threats, we're building our product. Then we generate codes. We require mandatory that such development should include tests, because it helps us to do the third point, dynamic analysis. In the kernel, we support sanitizers. We can automatically, in CI, run our tests and detect errors which block certain changes. So in CI, we support static analysis. We experiment with different static analyzers and get good results. And this is also an important condition for coding. And when we get all the CI benefits, reviewers come in who ask crazy questions, what if questions, actually. Every company uses all these stages, and we have also some interesting stages which few companies actually use. Before releasing, we give the ready-made product to our own internal team who does positive hacking. It's our internal team in Kaspersky, and that is a very important step, because I am a developer. I never tried to break anything. So penetration testing is different, and those people have quite a different mindset, and they can generate some crazy ideas which you as a developer would never think about. And there is one more test. We ask an external company to test our security. Of course, the external team doesn't have access to all our source code. They use different tactics, different approaches, and this is rather interesting too. And then we go to production. This is the last stage. In production, We also have some other people who try to find vulnerabilities in the code with their own tools, with their own hands. At one of the penetration tests, our pen testers found something. I like Jack Nicholson here. Those people are not that dangerous because it's defensive penetration testing, and difference between offensive and defensive is clear. Offensive find one vulnerability and exploit it. Defense testing has a more complex task. They will have to find all kind of vulnerabilities and offer protection. But before I talk about the vulnerability, let me tell you about Futexes. Futex is a fast user text. It's in Linux. It has been there for about 20 years. It implements synchronization primitives very efficiently. What is it? So there is an atomic variable which can support atomic operations. And to capture synchronization object, you shouldn't go to the kernel. You need the kernel only if you have contention. If somebody else tries to use your synchronization object. If nobody else tries to do that, so it's enough to use the atomic operation. But in the contention case, you have to go to the kernel, and in the kernel you have the Futex object with metadata and the query, which is waiting, the queue line, waiting line. And there are 4 APIs. 2 of them manage the Futex object. So you have to take it, and then when it is no longer needed, you have to release it, make it free again. And second is just the waiting line, wait and wake. They are waiting for the object to be freed. So it's a large subject. I recommend Ulrich Drepper's article, so there is a link in this QR code. He is talking about Futexes. It's very, very interesting indeed for you to realize how the kernel processes the primitives of synchronization. Windows also uses Futexes. Now let me talk about the vulnerability without any additional features. Let me demonstrate the exploit as such. How do you like it? What happens here? We create 2 threads. One of them calls wait, the other in parallel frees it. That's all. The kernel crashes. There is a strange thing here. Maybe you noticed it. Right here. Did you remember I said when to work with Futex you have to highlight it? It doesn't happen here. We're just waiting for it, and that is all. Why so? Because some time ago we had the user space on a legacy code, which allowed us not to call the object of synchronization, but just took them and used them. And it's easier for us to put it into the kernel rather than rewrite the whole code. As a result, we have such a strange feature when a futex object can be just used without initialization, without building it. Let's try to show you the block diagram to realize what is wrong here. If this is the futex-way algorithm. It checks whether the futex exists or not. If not, it exists it. If it exists, it takes a link. If the value is equal to the expected, the value which we sent, then we just get out. If not, then we add the object of synchronization into the queue and sleep, go to bed, thinking that when the synchronization object is finished, we shall be woken up, we're going to free the link, and somebody else will be able to use it. Actually, it's difficult for me to write such schemes, so this scheme looks better to me. How does the counter change its value? There were two threads. One calls futex wait, the other calls futex free. When you start futex wait, it provokes creation of futex in the kernel, and that object is created with a counter equaling 1. Then the futex free founds it, gets it, increases the value to 2 because he took it, releases its own link, and releases once again the link to the object because it believes that that futex object has the number of links equaling 2. Because it was 1, then 2, somebody slept, so it should be 2. He releases, it's 0 at the counter, and the object becomes free. However, the futex wait at that moment wakes up. It was sleeping all that time. It wakes up. It has a link to that object. And before getting out, he must reduce the number at the counter. And here we already have 0, and the kernel crashes. But in the worst case, we call it the decrement of free memory. Such vulnerability gets local privilege escalation, and let me tell you why. How can we exploit this vulnerability, and how can we force the system to execute your code? So we have to take the attacked object, and that object should get to the place where freed memory block was located. It's a non-trivial task. It looks like a sniper shot. Memory spraying is one of the methods. When a user provokes creation of a large number of objects in the kernel which fill all the free memory, and thus one of them will be right. And the allocator has very few cells, memory cells, to choose. It's interesting. We don't often focus on that. Microkernels have smaller attack surface and so on, but one of the interesting features of a microkernel is that it works with much fewer number of object types. As a result, it's finding the right object with the right size and squeeze that object into the place which was just freed, it's more difficult than in the usual Linux kernel when we have a lot of objects that the kernel manages. For example, we found such object. It's a matter of time, actually. It should not be just an object. It should be an object with a certain pointer to the buffer and with the size of the buffer. We can create a decrement of the freed memory. We can make such a way that the buffer size could be incorrect. We can apply decrement several times and get any value. For example, overflowing from 0 upwards. We created all f's, we used all the possible values. What do we get as a result? Buffer overflow. In Intel platforms, the stack goes back to the right until 0. You can see in the local variables we can have a certain buffer, but it is huge. What happens when we start filling that buffer with data? We reach the function return address and rewrite it. We control the buffer and we can rewrite it with something interesting. And in fact, the classic attacks are finished at this point. In the old times, when this technique was used, we didn't have any protection against. We didn't have execution prevention, EP, as Microsoft puts it. You could just rewrite the buffer code, and that is the window which allows you to execute your own code. Now we have execution protection, and you have to bypass it somehow. The bypass, one of the methods is return ROP. We have controlled return addresses in the stack, and we can make a chain of event which will execute the functionality that we need. And if we have a lot of functions in the code, we can take simple functions which end with instructions that we need. And we can take as many addresses as possible in the stack, and we can make as many tails of the functions as possible. And we can have a chain of instructions that are going to execute the functionality that we need. This is the situation that our code is executed at the kernel level. How did we eliminate that bug? Everything is obvious. It's just an error of calculation. When Futex Wait creates an object, he should create it with number 2, because one value had already been necessary before. The other point is added by the Futex Wait instruction, because it takes that feature temporarily. We can just correct initialization of object in Futex Wait. Initially, the number of links is 2, then free makes it 3, then 2, then releases it, makes it 1, and when wait addresses it, the value is 0, the object is free. Exploit doesn't work. Or does it? Did you notice an error in my calculations? Yes, of course. Let's look at the code, Futex free. It's a trivial code actually. I liked this line very much. The comment is true. The wait list should be empty, but we didn't check it, and there is no guarantee that it is really empty. So, let us fix that thing as well. This is the algorithm, Futex free, initially. First of all, we check that Futex exists. If it doesn't exist, we return the code. If it exists, we take a link, we release it once, twice, and that is all. To cover all the cases with unbalanced Futex alloc and Futex free, so we cannot control what is at Futex alloc and Futex free. We added one more sign here, one more parameter, and when we work with Futex, we check whether there is a flag. If there is no flag, we return the code. It's an error, and we prevent the calls to the object which was not obviously created, explicitly created by Futex alloc. If so, then we delete the flag. We need it in order to avoid repeated calls to that Futex. At this time, everything is all right. We eliminated 2 bugs, but we are thinking now, can we do something else for such errors to be impossible? How can we make them impossible? What are the lessons to be learned? Everything we did later with Futex, we rewrote Futex system as a whole because we realized that in each moment of time we needed no more Futex objects than we have in the flow. The data flow may be sleeping on one Futex only at each moment of time. So, what did we do? First, we inserted the Futex object into the flow object, and thanks to this new scheme, Futex can sleep only with one, the flow can sleep only with one Futex. It gives us a very important by effect. Right now, we cannot explicitly create and release those objects in the kernel. Their life cycle is linked to the life cycle of the flow object. As a result, we eliminated 2 APIs from the kernel. And now our subsystem looks like that, twice as simple as before. That is very important indeed, because thanks to this change of the logic, we didn't lose the functionality. And secondly, we eliminated the possibility for the user to manipulate the life cycle of the object. He doesn't have the levers that he had before to put the system into an undesirable state. This perhaps is the most important outcome of this event, of fighting this vulnerability. We can design code in such a way that would eliminate some of the states in principle. Certain time has passed, and we worked more, and we tried to prevent similar types of attacks. Let me tell you about all those technologies. Stack canary is a value which the compiler puts into the stack at the beginning and check at the output. What is the meaning? This canary is at the addresses higher than local variables. Then if the buffer is overflown, that canary is rewrote in the first place. We detect it and panic at once and prevent further spreading, further development of the attack. Now, kernel address space layout randomization. All objects in the kernel are placed at random addresses. At each uploading, at each boot, objects are placed in different places, and the hacker cannot build the chain for sure, because he can never tell where the chain is located. He has to guess, but it takes time and effort. It's a non-trivial task. Safe unlinking. We use it in the Windows kernel. The idea is quite simple. When you delete elements from the list, you check that the pointers for the previous and the subsequent elements are still valid. It's simple, and it helps you to detect damaged memory. If we had it before, then it would help us a lot. If memory is corrupt, so we panic. SMEP, Super User Mode Execution Prevention. It's for Linux. In Intel, the kernel can use user space, and some attacks become possible by replacement of addresses for the addresses in user space. We prohibited that. SMAP, Super User Mode Access Prevention, also for Intel. It prevents write access and read access to user space. Historically, it's strange for Intel. One more interesting thing is fuzz testing. It's a separate subject. As such, I can tell you a lot about it, but the essence, the meaning is that it helps you to check the states, put the system as such states that the person couldn't invent and test. We found a lot of interesting things there in my next presentation. And to conclude, I can tell you that it's important, very important, when you generate safe code, to design it in such a way that the user would have as little variation, as few variations as possible, as few capabilities to manipulate the kernel and the kernel structures as possible. Dynamism and variations are bad for users. And pen testers are good people. Please invite them at the stage of code generation. After I finish my presentation, please go to this link and evaluate it. That's all for me. Thank you for your attention. I'm ready to answer your questions. Andrei, thank you for your presentation. You had a slide with rope chains. The technology of high entropy, scatropy, randomization, does it prevent you from doing what? What do you mean? It's very difficult to guess the return address to build such a chain. Yes, the randomization of address space prevents building such chains because you never can tell what the address actually is. So it doesn't prevent him from attacking. There are some workarounds, but at the moment when we defined it, we didn't have such methods at all. So I listed the technologies which helped us to hinder certain types of attacks, including the one I mentioned, and to continue. What kind of protection measures do you have to use? Can you go into detail? How can we prevent exploits?
Okay, there are quite a few. I particularly like the Intel set technology. ARM has a similar technology. The idea is that there's a certain stack that is maintained by hardware, and the hardware will monitor that there are pairs between calls and returns. Because with ROP, what ROP is about is that we get a return without a call in the function. And there is a hardware technology that helps monitor that. I didn't mention that because we develop a product for particular projects with particular platforms which don't have such hardware support. I guess you had more focus on Intel platform. Yes. What about ARM, MIPS, those platforms? ARM has a similar hardware technology of monitoring the stack of calls. There's technology for access control, and there's the technology of address space randomization. It is hardware agnostic. Software canary is also software agnostic. Safe unlinking, likewise. It's a software technology, not a hardware one. Thank you for the question. Good afternoon. Thank you for the presentation. I enjoyed it. Especially, I liked your final solution, which is simple but quite elegant. When you looked for this problem, did you have an idea to have a counter of current links to the futex? And if yes, then why did you not do that? Answer: we had a counter of futex links. It's just a coincidence of two errors. One with the counting of links with lazy futex allocation, and that sort of was confusing. And the second one is that the paired nature of those calls was not monitored. What you mean is addressing the issue with one flag. What we want to address is to have for one futex alloc one instance of futex free. Good afternoon. Thank you for the presentation. I have a bit of a provocative question. Did you have, in retrospect, an idea to not implement sort of crutches for the kernel to avoid doing all of those things? Yes. Answer: yes, I did have such ideas. So legacy is bad. Don't do that. Don't use legacy. Thank you for the presentation. My question is this. At the time of planning of development of this software, did you have ideas of using a technology to have fewer problems with memory? Well, when this project was starting, Rust was in a very nascent stage. But Rust is a good language, I like it. But the problem is that there is not a very mature ecosystem yet for validating the Rust code. As far as I know, there are no tools yet to do a formal validation of Rust code. Whereas for C, for example, you would have a lot of such tools. I guess at some point we'll want to experiment with Rust. I like the language, I believe it's very promising, but at this point in time we develop with C because there are a lot of tools and practices and approaches. And importantly, we do development with certification in mind, and the certifying authorities like C and don't like other languages because they don't know how to work with them, because they have their own tools and practices to work with C. And for the newer languages, they don't have such a tool set available. Okay, thank you. Thank you for the presentation. A question a little bit off the topic, perhaps. You said that you divide pen testers into attack and defense. And you say that you expect exploits from attackers and you expect defense from defenders. Don't you expect exploits from defenders? They might write an exploit, but often that's quite an onerous task. And they don't report to me, they report to somebody else. So they can only do something on their own initiative. Sometimes they show us some exploit development concepts, some proof of concepts, but only, I guess, because they find it interesting. But designing exploits takes time and resources, and it's not a trivial task. So often the way it works is that they would demonstrate to us that you have a weak spot here, and in theory it could be exploited in this or that way. Thank you. And another question. You said that you started using fuzz testing to get to places where people don't go to otherwise. And yesterday there was a presentation on formal verification. Have you tried to look into that? That's a very good question. We do experiments with formal verification. We verified our IPC algorithm, which is inter-process coordination, using a formal model for a TLA class. But formal verification is very expensive. That is why we try to apply it in a limited way. Now we have limited application for it for very dedicated areas of the kernel. We have a separate team that does formal verification. And there they experimented with various queues and found errors in very widespread algorithms. So formal verification is cool, I like it a lot, but doing a formal verification of the full kernel is just unrealistic at this point.
Вопросы завершились, а ты можешь выбрать.
Okay, I guess these are all the questions, and now you can select the best one, and we'll give a present to the author. I liked the question about formal verification. This is a wide topic, which I believe is the future. Thank you for the questions. Okay, let's put out.